Hi folks. Now that we know what solutions are, we need a way of kind of measuring and indicating how concentrated they are. So this next topic is concentration. And concentration is a measure of the amount of solute in a given amount of solution or solvent. Okay, we want to know how much stuff is dissolved in a certain amount of solution or solvent. There are two main ways we're going to use to express concentration, and those are molarity and molality. Do be on your guard against confusing these two words. They are very similar, molarity and molality. Molarity is abbreviated with a capital M, and molality is abbreviated with a lowercase italicized m, right? A regular M would mean meters. And so we use this kind of fancy, more cursive looking M for molality. So let's look at each of these in turn. We'll look at molarity first. Molarity is the number of moles of solute in 1 liter of solution, of the whole solution. This is going to make it different to molarity, so I'm trying to really draw your attention to this right now. The whole solution. So here it is in equation form. Molarity is moles of solute divided by total volume, the volume of the whole solution. That whole solution includes the solvent and the solute together. And again, as I said, this is going to be different with molality, so I'm just drawing your attention to this now. So if you have 0.25 moles of sodium chloride in 1 liter of solution, what is the molarity? Molarity is the moles of solute divided by the total volume. The moles of solute is given to me. It's 0.25 moles. The total solution, the total volume of solution is given to me because it says in the problem that this is 1 liter of solution. So I divide by 1 liter of solution, and the molarity is 0.25 moles. Notice before we start doing more of these problems is that molarity can be rewritten it can be symbolized with a capital M, but it can also be written moles per liter. Sometimes you'll also see moles per decimeter cubed, but we'll stick to moles per liter in this class. So when you see the capital M, it actually means moles divided by liters. We've just given it an abbreviation so that you don't have to write it out that way, but sometimes writing it out that way actually makes it easier to remember the equation, moles divided by liters. So if we have 3.50 liters of a solution that contains 90.0 grams of sodium chloride, how do we calculate the molarity of the solution? Well, we know molarity equals number of moles divided by liters. But I wasn't given the number of moles. I was given grams of sodium chloride. I was given liters, so I know I'm going to put 3.50 liters in the denominator here, but I don't know how many moles to put in the numerator. I have to calculate those moles using grams. I know that number of moles equals mass divided by molar mass. Or if you prefer to think of it in terms of dimensional analysis, if we start with 90 grams, how do we convert from grams to moles? We divide by the molar mass in grams, and that lets us convert to 1 mole. So it's 1 mole over how many grams. The formula for sodium chloride is NaCl. So if I look up sodium and chloride on the periodic table, I get a molar mass of 58.44 grams, is the same as 1 mole. And grams cancel out. I'm left with moles, and I have 1.54 moles. So this is the value that I plug into the top, 1.54 moles. And my calculator tells me the answer is 0.44 molar. However, I have 3 sig figs divided by 3 sig figs. Therefore, I should report my answer to 3 significant figures as well. And the correct final answer is 0.440 molar NaCl. Let's try another example. You have 0.8 liters of a 0.5 molar HCl solution. How many moles of HCl does this solution contain? We know that molarity equals number of moles divided by liters. In this case, I don't know the number of moles. I'm trying to solve for moles, but I do know my number of liters, 0.8 liters, and I do know my concentration of in molar, 0.5 molar. Now, this is one of those situations where writing moles per liter will probably help us more than just writing the capital M. Because what I need to do is I need to get moles all by itself on this side of the equation. You can solve for x if you want to think of it that way. So I need to get rid of this 0.8 liters. I'm dividing x by this 0.8 liters. So the opposite of division is multiplication. So I'm going to multiply both sides of the equation by 0.8 liters. And when I do that, the 0.8 and the liters cancel out on this side, and I'm left with x all by itself. And on this side, the liters cancels out with the liters. So I just have 0.8 times 0.5, which is 0.4, and my units are moles. And this only has 1 sig fig, but that's appropriate because the other numbers in the problem only had 1 sig fig. So 0.4 moles of HCl is the final answer here. How many grams of potassium phosphate are required to prepare 250 mils of a 1.5 molar solution? Okay, this time I want to know grams, and we've already been reminded before that we can convert pretty easily between grams and moles. So when I write down my equation, that concentration in molar equals moles divided by liters, and I see that I've got a concentration and I have a volume. Ooh, this volume though is not in liters, it's in milliliters. So I'll need to convert this first. Milliliters to liters, you need to divide by 1,000 because 250 milliliters, there are 1,000 milliliters in 1 liter. So that means 0.250 liters. I'm going to solve for moles, and then in a separate step I'll convert that to grams. I have a 1.5 molar solution, 1.5 molar. And again, you may prefer to write that as moles per liter, so that when you multiply both sides of the equation by 0.250 liters, you can see that the units cancel out and you get as your answer 0.375 moles as your number of moles of potassium phosphate. Now, in this example, this is really only accurate to 2 decimal places. Because I only have 2 sig figs here in my concentration. So I generally don't round until I get to the final answer, but if that confuses you, you can go ahead and round now. You just get a slightly different answer in the end. So let's use this 0.375 moles of potassium phosphate to calculate how many grams of potassium phosphate we have. So 1 mole of potassium phosphate. If you look up potassium, 3 potassiums, 1 phosphorus, 4 oxygens on the periodic table, you get a molar mass of 212.27 grams of potassium phosphate. And when you do the multiplication, your calculator gives you the answer of 79.601 grams. And rounding to 2 sig figs, that will round off to 80 grams of K3PO4. So now, if you know ahead of time how much solution you want to make and what concentration you want that solution to be, you can figure out exactly how much you need to weigh out. Let's do one more example. How many grams of sodium chloride are required to make 500 milliliters of a 1.54 molar sodium chloride solution? Like the last problem, we're trying to calculate grams. So first we'll use our concentration equation, and then to solve for the number of moles, and then we'll have to use dimensional analysis to convert from moles to grams. I have a 1.54 molar solution. I don't know how many moles we're using, but I know that I have 500 milliliters. Notice the decimal point, this has 3 sig figs, and that is going to be equivalent to 0.500 liters. 0.500 liters when you divide by 1,000. So I'm going to multiply both sides of the equation by 0.500 liters. Again, if you prefer to think about that capital M as representing moles per liter, you can see the liters disappear when I multiply both sides of the equation by 0.500 liters. The liters cancel out. And you get, as your answer, 0.770 moles of NaCl. And now we have to take that value and determine how many grams it is equivalent to. We've determined already today that 1 mole of NaCl has a molar mass of 58.44 grams. And so the calculator says my final answer is 44.9988 grams. But we're going to round that to 3 significant figures. So that rounds up to 45.0 grams of NaCl. So these example problems all solved for concentration in terms of molarity.